Yo, welcome to Physics with Dipole. Hi, I'm Dipole and I'm back with a free lecture from the high-level problem-solving course that I'm launching for JEE Advanced and Olympiads. तो ये जो course है that has been inspired from a rare and prediction series from my YouTube channel. अगर तुम नए हो यहाँ पर, you can check out these playlists, rare series and prediction series. जहाँ पे मैं बहुत different kind of questions लेकर आता हूँ, different kind of techniques, short methods for solving questions faster, which has received a lot of praise from toppers of the last few years. टॉपर्स मतलब डबल डिजिट रैंकर्स, सिंगल डिजिट रैंकर्स. तो इन्होंने मुझे बहुत अच्छा फीडबैक दिया, सो आई हैव डिसाइडेड टू ब्रिंग आउट अ फुल फ्लेज्ड स्ट्रक्चर्ड कोर्स इंस्पायर्ड फ्रॉम दीज एपिसोड्स दैट आई हैव बीन पुटिंग आउट ऑन यूट्यूब. तो इस फ्री लेक्चर में एग्जैक्टली हम क्या करेंगे उसका एक ब्रीफ आउटलाइन दे देता हूँ, सो यू विल गेट एन आइडिया ऑफ हाउ द लेक्चर इज गोइंग टू फ्लो. तो इन दिस लेक्चर आई एम गोइंग टू टीच यू और आई एम गोइंग टू टॉक अबाउट द मोशन ऑफ अ चार्ज, ऑफ एन इलेक्ट्रिक चार्ज in the presence of an electric dipole. ये बेसिक थीम है इस लेक्चर का. बेसिक थीम मतलब इस पे बेस्ड हम वी आर गोइंग टू डू वेरिएशंस ऑफ कॉन्सेप्ट्स, वी आर गोइंग टू इंट्रोड्यूस सम कॉम्प्लेक्सिटीज. सो सबसे पहले मैं जो करूँगा वो है कि एकदम सिंपल सा सिचुएशन जहाँ पे मेरे पास एक डाइपोल है, उस पे उसके एक्सिस पर एक चार्ज है, एंड आई एम गोइंग टू आस्क यू हाउ डज द चार्ज मूव. ऑलराइट, कि पोजीशन ऑफ द चार्ज एज अ फंक्शन ऑफ टाइम. फिर इसमें एक वेरिएशन लेकर आएंगे जहाँ पे डाइपोल इज ऑल्सो फ्री टू मूव. तो फिर वो डाइपोल भी रिपेल हो सकता है अगर ये चार्ज पॉजिटिव है तो, ओके, नेगेटिव है तो अट्रैक्ट करेगा. बट देन यू विल हैव टू अकाउंट फॉर द मोशन ऑफ द डाइपोल एज वेल. देन एक बढ़िया सा ओरिजिनल क्वेश्चन विच आई रियली इंजॉयड फॉर्मुलेटिंग एंड देन ऑल्सो सॉल्विंग, कि जहां पर मेरे पास एक डाइपोल है एंड उसके सामने एक चार्ज है, तो चार्ज को इस तरीके से वेलोसिटी दे देते हैं, बट देन डाइपोल को रोटेट करते जाते हैं अपन. वी आर कंटिन्यूअसली रोटेटिंग द डाइपोल सो दैट इट्स ऑलवेज पॉइंटिंग टुवर्ड्स द चार्ज. तो चार्ज का ट्रैजेक्टरी किस तरीके से होगा, डिस्टेंस एज अ फंक्शन ऑफ टाइम, किस तरीके से हमें इसके एंगुलर वेलोसिटी को रखना पड़ेगा एज अ फंक्शन ऑफ टाइम सो दैट इट ऑलवेज पॉइंट्स टुवर्ड्स द चार्ज. ऑलराइट, सो दिस इज अ क्वेश्चन दैट आई फॉर्मुलेटेड बाय माय सेल्फ. इट्स एन ओरिजिनल क्वेश्चन एंड इट्स अ वेरी क्रिएटिव क्वेश्चन. इसको एनालिसिस करेंगे एंड यू विल सी हाउ दीज आर ऑल कनेक्टेड. You will see a common equation appearing in all of these आगे जाके भी. Alright, so it's not as if मतलब the lecture is going to flow very smoothly and very naturally. इसके बाद I'm going to solve an IPHO problem. And you might wonder कि यहाँ पे IPHO problem क्यों solve कर रहे हैं? Because ऐसा नहीं है कि कोई बहुत difficult question है. You will be able to solve it even on your own. I'm very confident once you've understood the first couple of problems that I've done. Because उसी तरीके से ऐसे flow करके हम इस problem को solve करेंगे, because उसका जो underlying basis होगा, underlying concepts होंगे, वो इन problems में हम already सीख चुके होंगे. Okay, then comes the gem of this entire lecture. The most beautiful part of this lecture is a very rare concept that I studied from a research paper जो अमेरिकन जर्नल ऑफ फिजिक्स में आया था कई साल पहले. तो वेरी रेयर कॉन्सेप्ट जिससे विच इज़ वेरी अननोन टू पीपल, बहुत कम जनों को पता है इस दुनिया में, एंड आई एम नॉट एग्जैजरेटिंग. तो इस रेयर कॉन्सेप्ट में लेकर इसको हम सीख कर वी आर गोइंग टू सॉल्व अ मोर कॉम्प्लेक्स क्वेश्चन जहाँ पे द डाइपोल इज फिक्स्ड एंड उस चार्ज का मोशन किस तरीके से होगा. तो दिस इज अ मोर कॉम्प्लेक्स क्वेश्चन कंपेयर्ड टू दिस, because इस केस में हमेशा डाइपोल इज ऑन द एक्सिस, a charge is always on the axis of the dipole, so it's a little bit straightforward compared to this. ये इस क्वेश्चन में डाइपोल के एक्सिस पर नहीं है हमेशा चार्ज. द चार्ज इज ट्रेवलिंग इन 2 dimensions. Okay, so we are going from 1 dimension, we are flowing and we come to 2 dimension, but you will see the same equation appearing again and again as we go from the very first simple situation to this very complex situation. बट ये रेयर कॉन्सेप्ट जो मैं सिखाऊंगा उसको यूज करके इस कॉम्प्लेक्स प्रॉब्लम, 2 dimensional प्रॉब्लम को भी हम इजीली सॉल्व कर लेंगे. ओके, दिस वाज फ्रॉम अ रिसर्च पेपर दैट आई स्टडीड थरोली. ओके, फिर इसी रेयर कॉन्सेप्ट को यूज करके एक और हम प्रॉब्लम सॉल्व करेंगे जहां पे एज यू नोटिस यहाँ पर हमेशा हमने चार्ज को डाइपोल के एक्सिस पर रखा है, बट इन दिस प्रॉब्लम वील कीप द चार्ज ऑन द इक्वेटोरियल प्लेन ऑफ द डाइपोल एंड देन वील एनालाइज द मोशन एंड अ वेरी सरप्राइजिंग ब्यूटीफुल ट्रेजेक्टरी कम्स आउट. But then the trajectory comes out using this rare concept that I'm going to teach you here. This is the star of this lecture. And then एक और यूरोपियन जर्नल ऑफ फिजिक्स में एक पेपर पढ़ा था मैंने, उस पे बेस्ड एक क्वेश्चन बनाऊंगा मैं for when the charge is जो चार्ज का मोशन इज परपेंडिकुलर टू द प्लेन ऑफ द परपेंडिकुलर टू द एक्सिस ऑफ द डायपोल, वो देखोगे तुम. एंड फाइनली एक ओरिजिनल क्वेश्चन जिसमें चार्ज फिक्स एंड डायपोल मूव कर रहा है. यहाँ पे सब डायपोल फिक्स था, या मतलब चार्ज का मोशन हम एनालाइज करते हैं. ये लास्ट क्वेश्चन में जो करूंगा उसमें हम डायपोल का मोशन एनालाइज करेंगे. ऑलराइट, सो यू आर गोइंग टू सी द लेक्चर फ्लो ब्यूटिफुली एंड वेरी स्मूथली इफ यू हैव वॉच्ड एनी ऑफ माई फुल लेंथ लेक्चर्स जो मैंने यूट्यूब पे भी डाला है, लाइक न्यूटन्स लॉज या काइनेमैटिक्स. You will see you will know the way I structure the lecture is it's all connected from the first to the next to the next. तो ऐसे एकदम smoothly flow करता है. Alright, and before you know it, you will be solving high level problems. तुमको समझ में भी नहीं आएगा कि वो एक difficult problem है जो तुमने solve कर लिया. Alright, so I hope you enjoy the lecture. एकदम आराम से बैठ के देखना. Definitely ये वाला part तो देखना ही देखना because ये बहुत कम जनों को पता है इस दुनिया में. Alright, enjoy the lecture. And I will see you next time, and I will see you at the top. Let's talk about the motion of a point charge in the field of an electric dipole. So for that, let's quickly recap the field and potential of an electric dipole. So suppose I have a dipole here, electric dipole. I'm going to assume this electric dipole to be very tiny. So iska matlab it's going to be extremely small, like almost a point object. So at an angle theta, at a distance r, the potential due to this dipole is Kp divided by Kp cos theta divided by r square, where K is 1 by 4 pi epsilon naught. And if I take this as r cap and this is my theta cap, so these are my unit vectors. The radial component of the electric field is, you can just calculate it on your own by taking the derivative del V by del R. ये मिल जाएगा 2kp cos theta by r cube, and the tangential component minus del v by r del theta would be kp sin theta by r cube. Okay, so these are the basic concepts of potential and field, the basic values of potential and field that will be useful for us when we analyze the motion of a charge in a dipole. Okay, so we are going to start off with a simple one-dimensional problem, and then we'll increase the complexity and go to two-dimensional setups. All right. So let's go ahead. So let's do a simple question where I have an electric dipole that is fixed, and on its axis I have a point charge of charge q and mass m, and let's assume initially that the point charge is positively charged, and then we later on talk about if it is negative. So initially the distance of this point charge from the dipole is some constant b, and initially the velocity of the point charge is 0. Here r dot means dr by dt. It's just a label for dr by dt. So dr by dt, velocity of the point charge, initially 0. So we've released this point charge from rest on the axis of a dipole, and I want to find the distance of this charge as a function of time. Okay, so r is the distance of the charge from the dipole. Alright, so let's do this question. Honestly, it's very straightforward. What we can do is we can conserve the energy, and by conserving energy we'll get the velocity. I'm just outlining the solution of how we are going to proceed. We'll conserve energy, we'll get the velocity of the point charge, we'll write velocity as dr by dt and integrate. That's it. Okay, but we will then go on to more complex setups in 2 dimensions. Alright, so let's quickly do this. So the energy initially is, I can write the potential of the dipole into the charge as the energy initial, because initially kinetic energy of the charge is 0. So the potential on the axis would be kp by r squared. So initially it would be kp by b squared, the potential of the dipole, into the charge q. So this is the potential energy initially, and at some general instant the potential energy would be kp q by r squared plus half m r dot square. R dot is the velocity of the charge. Okay, so all we have to do is integrate. So let's quickly do this. So I have r dot squared is 2 by m times, let me just take kpq by b squared as common. So I'll have 1 minus b squared by r squared, right? So let me just label this as some, let me just call this some v infinity squared. Why am I doing this? Because this is in fact the square of the speed at infinity. If this is a positive charge and if it goes to infinity, this will be its speed. Can you see that? Because you can just quickly see from this equation itself, as r tends to infinity, this is going to be the speed square of the speed. So I'm just labeling this as v infinity squared. Or you can just see it from energy conservation also. At r tending to infinity, the potential energy will be 0. All you will be left with is the kinetic energy, and you can see r dot square would be 2 kpq by mb squared at infinity. So I'm just labeling this as v infinity squared. Okay, so it'll just be a little convenient. Alright, so I'll have r dot squared is v infinity squared times r square minus b square divided by r squared. So if I just take the square root on both sides, now it's a simple integral. So I'll write r dot as dr by dt and take all the r terms on one side. So r by r square minus b square dr. See here, when I took the square root, I have to take the positive sign. I can take the negative or the positive sign in the square root, right? The reason I did that is because if I assume the charge to be positive, we are assuming the charge to be positive, the distance is going to increase. So r dot has to be a positive number. All right. Okay. So now I'll have, what do I have? And I'll have v infinity times dt. At t equal to 0, the distance is b. At general t, the distance is r. Now this integral should be very straightforward. I'll just write down the integral. So I hope all of you know how to integrate this by substitution. Just substitute r square minus b square as some u squared, where u is some new variable, and you will get this. Okay, so this is basic integral. Should be v infinity into t. And therefore, by substituting, you will see r square is b squared plus, and therefore r is. Alright, so that is the distance of the point charge as a function of time. And you can see from this equation also, as t tends to infinity, this quantity will be a very large quantity compared to b squared. So as t tends to infinity, r will tend to v infinity to t, which is expected. Okay. Alright, so this is the distance of the point charge as a function of time, a very simple problem. Now here, what if the point charge was negative? What happens then? So if the point charge was negative, then here q would be negative, right? And then when I take the square root, I can't say this, I can't use this equation, because first of all q is negative, so there is no solution, there is no real solution for v infinity. And that makes sense, because if q is negative, it's not going to go to infinity, it's going to get attracted towards the dipole. Alright, so what I'm going to do is, for the negative charge, I'm just going to erase the steps from here on, and then we'll solve this equation forward for a negative charge and see what we get. Alright. Alright, so the equation till here is the same, it doesn't depend on the sign of the charge, whether it is positive or negative. Now, if we have a negative charge, so here we have q as negative. Alright, so let me just write this as minus 2kp mod q by mb squared. It's just a little easier to see. Right? I'm just writing q as minus mod q, so we'll deal with positive numbers. And then let me take this negative sign inside. So then I'll have b square by r square minus 1. Alright? And now let's do the calculation. So I'll have r dot squared is 2kp mod q by mb squared times b square minus r square by r square, and then I'll take the square root. Now, when I'm taking the square root, I have to take the negative root, because I know when I release this charge, it is going to go towards the dipole. So the distance between the dipole and the charge is going to decrease. So I have to take the negative square root. Alright, so that's something to keep in mind. Alright, so I'll take this r here. So r dr by dt should be this entire quantity, and let me just call this some v naught. Okay, Alright, so I'll take dt on the other side and I'll take this quantity here. Okay, and now we'll do the integral once again. So the integral of this is very similar to what we just did. So it will simply be negative right, 0 to infinity and b to r. Alright. Now, when you substitute, you will get b square minus r square should be minus v naught t, and therefore r square should be b squared plus, b squared minus. Alright, so this distance as a function of time comes out to be square root of b square minus v naught square t square. And now you can see that the charge will collide with the dipole in a finite time. In that finite time, let's say the charge collides at t equals b by v naught, where v naught is this entire quantity. I've labeled this entire quantity where v naught is 2 kp mod q by mb squared. Alright, so the charge collides at t equal to b by v naught. Alright, so the negative charge situation was also pretty straightforward. Just make sure that you take the negative square root here. Okay. Now, one thing that we must keep in mind, that in this negative charge situation, we've actually made an assumption, or you can say it's an approximation, that this dipole is an exactly, or is a perfect ideal dipole, which means that we have to treat it as an exact point object. Because the field that we write here, or the potential that we write, kp by r squared, the potential that we write for a dipole on its axis, this kp by r squared is actually for faraway points. But if we assume the dipole to be exactly a point object, in that case we can use this potential kp by r squared to be valid throughout the entire journey, right up till the point that the point charge collides with the dipole. Alright, so that's just something to keep in mind when we are dealing with a case where the charge gets near the dipole. If the dipole had a small but finite size, then this analysis would break down when we get near the dipole. Alright, because ultimately kp by r square is an approximation for finite dipoles. Alright, so just something to keep in mind. Okay. Now let's modify the question and allow the dipole also to be free to move. So now the dipole is free to move, it has a mass m, the point charge has mass small m, let's say we're taking the case where the point charge is positive, and they are both released from rest, and initially the distance between them is b, and both the dipole and the charges are at rest and free to move. And I want to find the distance between them as a function of time. Alright. So in addition to energy, there will be another quantity that will be conserved, which is the momentum. So we won't actually do the momentum conservation and the energy conservation, because the concept of reduced mass will make our problem very easy to solve without actually doing momentum conservation and energy conservation. We will still do energy conservation, of course. So one thing to realize is that the center of mass of the system is at rest initially. So of course it's going to be at rest at all times. There is no external force on the system in the inertial frame in which we are observing these to be at rest initially. So the center of mass is going to remain at rest. So the energy, we know in the center of mass frame for a two-body system, we can write the energy as half mu v relative squared, where mu is the reduced mass plus the potential energy. The kinetic energy of a two-body system can be written as half mu v relative squared, where v relative is the rate of change of the distance between the two bodies, and in this case it's a one-dimensional motion, so I can directly write v relative is the rate of change of distance, which is r dot, and mu is the reduced mass, so mu would be, right, so we know this expression, and of course this is going to be conserved. So the potential energy would still be at a general instant when the distance between them is r. The potential energy is still going to be kp by r square times q, potential into charge, and this should be equal to the initial energy. and V relative, I can just replace it by, alright. So you see that this expression is exactly the same expression that we had earlier when only the charge was free to move. In that case, we had small m, the mass of the charge, in place of mu. That's all. That's all we had. So when we transition from that problem where the dipole was fixed to this problem where the dipole is free to move, mathematically, all we have to do is replace the mass by mu. Alright, so that is exactly what we're going to do, and I can just directly, you can do the steps on your own if you want to, but I'm just going to save some effort, and I'm going to write the expression directly as r is equal to b squared plus v infinity squared t squared, and now in this case v infinity is the relative speed. It's not the speed of the point charge anymore, it's the relative speed, because what we got there, v infinity squared, was kpq, right? 2 kpq by mb squared is what we had gotten. So here now I have to replace m by the reduced mass, and you can see what is this? What is this? This is, if you set r tending to infinity, r dot squared would be 2 kpq divided by mu b squared, which is exactly this. So basically, as you take r tending to infinity, the value of r dot would be this value. The square of r dot would be this value. So basically, v infinity represents the rate at which the distance is changing between the two particles, or between the charge and the dipole, when the time is after a very long time, when time tends to infinity. Alright, so it's very straightforward. You can just do this calculation. You can do the steps on your own, but we've already done the mathematics, so we can just use this transformation to arrive at the final result. Alright, okay, let's go ahead. Now let's look at a question that I came up with myself, and it's a two-dimensional question involving the motion of a charge in the field of a dipole, and it's a very interesting question, and the solution is also very elegant, and I found it really interesting. I came up with it myself, and I was just thinking about creating problems for this topic, for the motion of a charge in a dipole field. Let's take a look at the question. So I have a point charge that is placed on the x-axis, and we have a dipole that is fixed at the origin. The point charge has charge q, mass m, and it is being given a velocity v naught perpendicular to the x-axis. Alright, this is at t equals 0. This is the initial situation. We have a positive charge, and now the dipole is rotated by some external agent. It is rotated with some angular velocity omega as a function of time, such that it always points towards charge q. So I want to find what should that function of angular velocity as a function of time be, so that the dipole is always pointing towards the charge. Remember that the charge is going to move under the influence of the field of the dipole, and the dipole itself has to be rotated so that it is pointing towards the charge. Okay, so it's I found it a very interesting setup. So let's analyze this. So what is going to happen if you just quickly want to visualize what is going to happen? The charge is going to get repelled away by the dipole. So because the dipole is always pointing towards the charge, at any instant when the charge is here, the dipole is going to be pointing here. When the charge goes to this point, travels further in time, the dipole is again going to rotate. Alright. So if I label this angle as theta, I basically want theta dot, the derivative of this theta. Alright. Now this theta is also the angle that the position vector of the charge is making. This is the position vector of the charge from the origin. So basically what I want to do is I want to calculate the position, the rate at which this position vector of the charge is rotating. So first of all, can you see that the force of this dipole on the charge will always be along the radial direction, because the charge is always on the axis of the dipole. So on the axis, the force by the dipole on the charge is always going to be, the electric field on the axis is going to be 2 kpq divided by r cube, right? Because we had the radial field as 2 kpq divided by r cube cos theta, and the tangential field had sin theta, but theta is measured from the dipole. So here the angle theta has to be set to be 0 at all times, because the charge is on the axis of the dipole. Okay, if you want to, let me just label this as phi so that there's no confusion between phi and theta. Here theta is measured from the axis of the dipole. Alright. Now, theta will be set to 0 for the points on the axis of the dipole, and therefore we arrive at this force as the field into the charge. Now can you see that this force is always in the radial direction? Because the tangential component of the field will be 0, because there is a sine theta term, and theta itself is 0 for the points on the axis. So this force by the dipole on this charge is always going to be radial, and therefore this is a central force motion. And central force motion means that because the force is always going through the origin, the force on this charge is always going through the origin, the torque about the origin is 0, and therefore the angular momentum about the origin is conserved. Okay, the angular momentum is conserved, and its magnitude will have a value of mv0 into b. Alright, I'm just writing it down here for if we need it later on. So we've established that this motion is a central force motion, and the angular momentum is always conserved. Okay, now in general, if I have this charge with some velocity v, I can break it down into two components. One is the component parallel to r, which is, I can write it as r dot, and the component of velocity perpendicular to r, which I can write it as r phi dot, right? The distance r into the rate of change of the angle, r omega r will be the component of the velocity perpendicular to r, and the rate of change of r would be the component of velocity parallel to r. Alright, so when I write the energy of the system, I can write it as half m v squared, so half m r dot squared plus this v perpendicular, let me write it as v perpendicular, plus v perpendicular squared, plus the potential energy. Now you see that this dipole force is this much, 2 kpq by r cube. So I can define a potential energy, because I know force can be written as minus du by dr. It's a central force, so there is no theta component, there is no phi component of the force. So 2 kpq by r cube, I can write the potential energy as kpq by r squared, because of course the derivative of this will give you back this, right? You can just integrate this to get this. Or of course you can also write potential into charge. Potential of the dipole is kpq by kp by r square into the charge. Alright, so I'll just write it here. Now what we can do, the key here is to express the perpendicular component of velocity in terms of the angular momentum. In general, I can write the angular momentum as m v perpendicular into r. When you take cross product between r and momentum, the position vector and momentum, only the component of the velocity that is perpendicular to r will survive in the cross product. So you'll end up with mv perpendicular into r, right? You can also write it as mr square phi dot, mr square omega. Okay, so I can replace this v perpendicular as L by mr. So here I can simply write it as L squared by mr squared. And therefore, you see what we will get is a very elegant result, that this can be combined with this term, because they both have r square in the denominator, and it will make our mathematics very easy. My total energy now becomes half mr dot squared plus, if I were to take kpq by r square as common, let me write it this way. Kp times 1 plus L square by 2m Alright, I'll talk about why I have written it in just a minute, but can you just quickly see that this expression is correct, mathematically at least. I've just taken kpq by r squared common, and therefore I'll have 1 plus L square by 2m and just divide by kpq. Alright, so the reason I have written it this way is because, let me just write this term. Let me just redefine this term. These are all constants. L is a constant, remember, as some P effective. Alright. So P effective is P times 1 plus L squared by 2m kpq. Alright. And therefore my energy, you'll see in a minute why I'm doing all of this. Half mr dot squared plus kp effective q divided by r squared. Now can you see that this is nothing but mathematically the energy of a one-dimensional motion of a point charge that is traveling in the field of a dipole whose value is P effective. So I have reduced this entire motion, entire two-dimensional setup to a one-dimensional problem, and it's a one-dimensional problem that we've actually already solved, because this is the energy of the charge at t equals 0. At t equals 0, what is the value of r? The value of r is b. And what is the value of r dot? What is the rate of change of the distance at t equals 0? 0, because the velocity is perpendicular to the position vector, and therefore the rate of change of position vector at t equals 0 is 0. So having this energy and having these initial conditions, can I get, or can you get the position, the distance, the distance of the charge from the origin as a function of time? We can, because we've already solved this mathematically for a one-dimensional situation, and the mathematics is going to be exactly the same. Alright, so let me just erase this part, and we're going to solve, and we're going to find the distance of this point charge from the origin as a function of time. But we are not done yet, because ultimately we want to find the angular velocity, but we have to do this intermediate step of finding r as a function of time, and then we'll use that to get omega as a function of time. Alright, so let me just first erase this. So we had my energy as half m r dot squared plus kp effective times q divided by r squared, right? And what was p effective? P times 1 plus L squared by 2m kpq. This was p effective. And because t equal to 0, at t equal to 0, the distance is equal to b, and the rate of change of distance is 0 initially. So I can just use what we've already done and say that distance as a function of time is going to be b squared plus v infinity squared t. Well, what is v infinity now? V infinity is basically the rate of change of distance when time tends to infinity. So v infinity would be, basically it is r dot at t equal to r dot at t tending to infinity. So how would I get that? Just set r tending to infinity. At t equal to infinity, this charge will be infinitely far away from the origin, so this tends to infinity, and therefore I can say that the energy, what is the energy? The energy is half mv naught squared plus kpq by b squared, right? This is the energy, half mv naught squared plus kpq by b squared. This should be equal to, after a long time, only kinetic energy will be possessed by the charge. The potential energy will tend to 0. All right. So we will get this equation. So I'll have v infinity. This equation will give you v infinity. All right. V infinity squared would become v naught squared plus 2kpq by mb squared. All right. So you will get r as b squared plus v naught squared plus 2kpq by mb squared times t. All right. Okay, so this is the initial energy that I've written here. The initial energy is the kinetic energy half mv naught squared plus the potential energy, which is kpq by b squared, and then I've equated it to the energy at infinity. So we've got the distance of the point charge from the origin as a function of time, but we are not done yet, because we need to find angular velocity. Now that is very straightforward, because we know angular momentum is conserved. So angular momentum is conserved, I can write L is equal to mr square omega, and therefore omega is L by mr squared. So we basically need r as a function of time, which is why we went to all of this effort in order to get r as a function of time. And what is angular momentum? M v naught b. So I will get v naught b divided by r squared, which is b squared plus. All right. R squared, I've just written it as b squared plus v infinity squared t squared, and this is my v infinity squared. Okay, so the angular velocity as a function of time is given by this simple equation. So it's a very interesting problem that I came up with when I was trying to think of some unique type of problems for this topic, and this turned out to be a nice central force motion. So it involves a lot of concepts. It involves the dipole field, and it involves how we deal with central force motions by converting the perpendicular component of velocity in terms of r by using angular momentum conservation, right? And then of course we did that neat trick by substituting by replacing that entire term by p effective, and then comparing this to our one-dimensional motion. All right. So I hope you've enjoyed this question. Just look at all of this carefully and absorb everything that I've just said. Now let's do a question from IPHO 2011. So let's read the question first. क्या बोला गया? To commemorate the centenary of Rutherford's atomic nucleus. So मतलब वो 100 year anniversary बोल दो. The scattering of an ion by a neutral atom. Okay, so an ion of mass m, charge q, is moving with an initial non-relativistic speed v0 from a great distance towards the vicinity of a neutral atom of mass capital M much greater than small m, and of electric polarizability alpha. Okay, तो क्या है ये वो बोला जाएगा क्वेश्चन में. The impact parameter is b. Okay, so यहाँ पे मेरे पास एक चार्ज है जिसको ऐसे प्रोजेक्ट किया गया है, एंड ये एटम का लाइन है parallel to the initial velocity, and this distance is b. ठीक है. So the atom is instantaneously polarized by the electric field E vector of the incoming approaching ion. मतलब क्या कि एटम में पोलराइज हो गया इलेक्ट्रिक फील्ड से. नेक्स्ट सेंटेंस देखो, द रिजल्टिंग इलेक्ट्रिक डायपोल ऑफ द मोमेंट इज P equal to alpha E. Alright, so basically this whole polarizability concept is that जितना इलेक्ट्रिक फील्ड है चार्ज का, उसके कारण डायपोल मोमेंट इंड्यूस हो जाता है एटम में, और कितना होता है? अल्फा ई. ओके, इग्नोर एनी रेडिएटिव लॉसेस. ठीक है. सो फर्स्ट प्रॉब्लम क्या बोला गया? 3.1 फर्स्ट पार्ट, कैलकुलेट द इलेक्ट्रिक फील्ड इंटेंसिटी ई वेक्टर एट अ डिस्टेंस r फ्रॉम एन आइडियल इलेक्ट्रिक डायपोल एट द ओरिजिन अलोंग द डायरेक्शन ऑफ p. सो ये तो बहुत ही स्ट्रेट फॉरवर्ड है. ऑल दिस इज आस्किंग अस टू calculate the field on the axis of a dipole. ऐसे मेरे पास डायपोल है and axis के along field कितना होता है? So field would be 2kp divided by r cube, where k is 1 by 4 pi epsilon naught. Alright, so this is the field. फिर next question में क्या बोला गया? So second part में क्या बोला गया? Find the expression of the force vector acting on the ion due to the polarized atom. Show that this force is attractive regardless of the sign of the charge of the ion. Okay. So यहाँ पर मेरे पास जो ion है उसका charge Q है. When it is at a distance r from the atom, तो atom पे इलेक्ट्रिक फील्ड कितना बन जाएगा? ड्यू टू द चार्ज, दिस इलेक्ट्रिक फील्ड ड्यू टू द चार्ज वुड बी k cubed divided by r squared, where k is of course 1 by 4 pi epsilon naught. एंड ये डायरेक्शन क्या होगा? अगर सपोज चार्ज को हमने पॉजिटिव मान लिया तो द इलेक्ट्रिक फील्ड विल बी इन दिस डायरेक्शन. सो इफ I take my position vector of the charge in this direction, तो उसको मैं minus r cap लिख सकता हूँ. Alright, so I am taking the position vector of the charge as r vector from the atom to the charge to the ion. So electric field is opposite to that due to the charge. नाउ दिस विल इंड्यूस अ डाइपोल मोमेंट इन द एटम, वो कितना बन जाएगा अल्फा ई, सो माइनस के अल्फा क्यू डिवाइडेड बाय आर स्क्वायर आर कैप, ऑलराइट। तो ये डाइपोल मोमेंट का डायरेक्शन क्या होगा, इसी डायरेक्शन में हो जाएगा, बिकॉज अल्फा को हम अल्फा को हम पॉजिटिव मानेंगे, ऑलराइट। तो अब अल्फा को पॉजिटिव क्यों मान रहे हैं, बिकॉज थोड़ा सा फिजिकली देख सकते हैं कि जो चार्ज है, अगर ये पॉजिटिव चार्ज है तो उसके इलेक्ट्रिक फील्ड के कारण इस एटम में इस तरीके से चार्ज सेपरेशन हो जाएगा। द नेगेटिव चार्ज विल गो टू द लेफ्ट, द इलेक्ट्रॉन्स which will produce a dipole moment to the right in the atom. Okay, so the dipole moment that is induced will be parallel to the electric field. All right, ठीक है। तो फोर्स कितना बन जाएगा, सो मुझे पता है कि द फोर्स ऑन द आयन, कैन आई राइट इट एज, बिकॉज द डाइपोल मोमेंट इज पॉइंटिंग इन दिस डायरेक्शन, उसका इलेक्ट्रिक फील्ड, द डाइपोल मोमेंट ऐसे है तो उसका इलेक्ट्रिक फील्ड एट द आयन वुड बी इन दिस डायरेक्शन, करेक्ट। सो फोर्स भी इस डायरेक्शन में, आई अज्यूम द पॉजिटिव चार्ज, ठीक है। एंड देयरफॉर फोर्स ऑन द आयन वुड बी 2kp by r cube into the charge, and it will be minus r cap, right? p is the magnitude, ठीक है। तो आई विल राइट, यहाँ पे ये सब्स्टिट्यूट करूँगा p का वैल्यू, तो मेरे पास आ जाएगा 2k squared alpha q squared divided by r raised to 5 with a negative sign on the ion. So this will be my force, ठीक है। Now I also have to show that the force is attractive regardless of the sign. तो जब चार्ज पॉजिटिव है वहां पे तो मैंने बता ही दिया कि फोर्स इज अट्रैक्टिव बिकॉज इट इज टुवर्ड्स द एटम माइनस आर कैप के कारण, राइट। बट अगर चार्ज नेगेटिव है तो क्या फर्क पड़ेगा, अगर चार्ज नेगेटिव होगा ये तो द इलेक्ट्रिक फील्ड विल बी इन दिस डायरेक्शन ड्यू टू द चार्ज, so therefore the dipole moment will be in this direction, and therefore the electric field due to the dipole on the charge will be in this direction, and therefore because the electric field is in this direction, r cap direction, and the charge is negative, the force will again be towards minus r cap, मतलब towards the atom. Okay, so the force is going to be attractive regardless of the sign. Alright, फिर third क्या बोला, what is the electric potential energy of the ion atom interaction in terms of alpha q and r? Now basically I can just use this and integrate it to get the potential energy. So potential energy कितना बन जाएगा, I can write F is minus du by dr, central force है ना, only radial component है, ठीक है। तो I can just integrate this, तो du would be minus f dr, तो नेगेटिव नेगेटिव कट के 2k स्क्वायर अल्फा q स्क्वायर, तो कांस्टेंट है तो आ जाएगा dr by r raised to 5. ओके, सो इन्फिनिटी पे पोटेंशियल एनर्जी जीरो मानूंगा एज इज आर स्टैंडर्ड कन्वेंशन, एंड आर पे पोटेंशियल एनर्जी कुछ u, तो u वुड बी इक्वल टू माइनस 2k स्क्वायर अल्फा क्यू स्क्वायर, r रेज टू माइनस 5 का इंटीग्रल इज माइनस r रेज टू माइनस 4. दिस विल बिकम माइनस k स्क्वायर अल्फा क्यू स्क्वायर डिवाइडेड बाय r रेज टू 4, ट्वाइस ऑफ r रेज टू 4. तो यहाँ पर k को you can of course substitute it as 1 by 4 pi epsilon naught, and you can get it in terms of epsilon naught. One thing here to note is that don't use the potential energy as minus p dot t or the potential into the charge. Potential मतलब minus p dot t मतलब the electric field due to the charge multiplied by the dipole moment, वो मत यूज करना, because यहाँ पर in this when you derive this or charge into potential of the dipole, वहाँ पे you assume that the dipole moment is a constant, Here dipole moment vector is not a constant, it's changing direction and it's changing the magnitude as well. So वेरिएबल है ना, आर पे डिपेंड करता है, डायपोल मोमेंट इटसेल्फ डिपेंड्स ऑन आर. सो बेटर टू डू इट बाय बेसिक्स बाय कैलकुलेटिंग द फोर्स एंड देन इंटीग्रेटिंग टू गेट द पोटेंशियल एनर्जी. ओके, अच्छा, फिर अब नेक्स्ट क्वेश्चन पे जाते हैं. Let's look at the fourth part of this question. Find the expression for r minimum, the distance of the closest approach as shown in the figure. तो यहाँ पे मेरे पास फिगर है एंड डिस्टेंस ऑफ क्लोजेस्ट अप्रोच निकालना मुझे ये. तो सबसे पहले तो कैन यू सी दैट द फोर्स इज ऑलवेज सेंट्रल फोर्स है. तो फोर्स ऑन द डायपोल was always along the was parallel to minus r cap, right? So force is an attractive central force and therefore angular momentum will be conserved. So can I say m v naught b is the initial angular momentum, should be, अगर यहाँ पे velocity में कुछ v minimum बोलूँ, v maximum बोलूँ, तो वहाँ पे हो जाएगा m v maximum into r minimum, right? वहाँ पे maximum speed हो जाएगा. तो एक इक्वेशन ये आ गया एंड दूसरा आई कैन कंजर्व एनर्जी, सो आई कैन राइट हाफ एम वी नॉट स्क्वायर्ड एंड इनिशियली तो इन्फिनिटी पर है, तो हाफ एम वी नॉट स्क्वायर शुड बी हाफ एम वी एम स्क्वायर्ड प्लस द पोटेंशियल एनर्जी. एंड जो पोटेंशियल एनर्जी है दैट वुड बी के स्क्वायर, लेट मी जस्ट राइट इट एज सम c by r raised to 5 r raised to 4. पोटेंशियल एनर्जी वॉज प्रोपोर्शनल टू आर 1 over r raised to 4 है ना, और c वो सब कॉन्स्टेंट्स था जो हमने निकाला था, वो मैं बाद में सब्स्टिट्यूट कर दूंगा. ठीक है, तो ये मेरा दो इक्वेशन हो गया एंड नाउ इट्स प्रीटी स्ट्रेट फॉरवर्ड. यहाँ पे r मिनिमम लिखता हूँ. तो नाउ इट्स प्रीटी स्ट्रेट फॉरवर्ड, ऑल आई हैव टू डू इज सॉल्व फॉर r मिनिमम. सो आई जस्ट एलिमिनेट vm फ्रॉम द फर्स्ट इक्वेशन एंड सेकंड इक्वेशन में मैं सब्स्टिट्यूट करता हूँ, तो मेरे पास आ जाएगा. तो सेकंड इक्वेशन को मैं लिख सकता हूँ v नॉट स्क्वायर इज, और लेट मी जस्ट राइट इट दिस वे, half m v naught squared should be half m, now v m squared को मैं क्या सब्स्टिट्यूट करूँ, v naught b by r minimum, ठीक है, माइनस c by r minimum raised to 4. ओके, तो इफ आई जस्ट मल्टीप्लाई द एंटायर इक्वेशन बाय r minimum raised to 4, तो ये बन जाएगा r minimum raised to 4 into m v naught square by 2 should be m v naught square b square by 2 into r minimum squared minus c. So we have a quadratic in r minimum squared, right? So let me just say कि let r minimum squared be some x. तो मेरे पास हो जाएगा, I'm going to just divide the entire equation by 2 by m v naught squared. Okay, so x squared should be equal to b square x minus 2c by m v naught squared. So I'll have x square minus b squared x plus 2c by m v naught square should be 0. अब इसको सॉल्व करते हैं, तो x का वैल्यू क्या आ जाएगा, देखो b प्लस माइनस b रेज टू b स्क्वायर्ड, सॉरी, प्लस माइनस b रेज टू 4 minus 4, this will become 8c by m v naught squared divided by 2. All right, now I have to choose the positive or negative sign, so let's just do that on the next page. Now we have to choose between the positive and negative sign. So see, this is, ये जो मेरे पास r minimum का स्क्वायर्ड है ये, अब जब मैं पॉजिटिव एंड नेगेटिव साइन के बीच में चूज करूँ तो I have to look at some special case. If I let c tend to 0, मतलब the potential energy is extremely negligible, मतलब the force is also very negligible, force of attraction on the ion. Suppose, मतलब मैं एक special case choose कर रहा हूँ, तो force अगर बहुत ही negligible है, almost 0 है, तो ion will just travel in a straight line. We expect that. So the minimum distance will simply be b, correct? So अगर c tends to 0, then r minimum must tend to b, right? And therefore we have to go for the positive sign here. ठीक है, नेगेटिव साइन होगा तो फिर तो वो 0 बन जाएगा r minimum. That is not possible. Okay, so therefore r minimum will come out to be b by root 2. इसको b by root 2 को मैं कॉमन ले लेता हूँ, तो 1 प्लस स्क्वायर रूट ऑफ b/2 को मैंने कॉमन ले लिया तो अंदर आ जाएगा 8c बाय mv0 square b⁴. All right, this is my minimum distance between the ion and the atom. Okay, let's go to the next question. So last part of the question पे जाते हैं. If the impact parameter B is less than a critical value B0, the ion will descend along a spiral to the atom. In such a case, the ion will be neutralized. The atom in turn is charged. This process is known as charge exchange. What is the cross-sectional area? Pi B0 square. So basically B0 का value निकालना है मुझे. So let me just quickly write down कि हमें R minimum का क्या expression आया था. So we had gotten B/√2 times 1 plus 1 minus 8c by mv0 square b⁴. This was the expression we got for the minimum distance. Now, जैसे ही you encounter a quadratic, always you should be mindful of the discriminant. The discriminant needs to be positive for real solutions. So यहाँ पर बोला गया कि if the impact parameter B is lesser than a critical value, तो जितना कम B होगा यहाँ पर, you can see this quantity will keep on getting bigger, and therefore there is a chance that the discriminant becomes negative, and in that case we won't have a solution for R minimum, and that is what the question is referring to. In that case there will be no R minimum and ion will descend along a spiral. All right, so for this condition, just at the critical value we'll expect that the discriminant should be 0. उससे ज़्यादा अगर B हो गया तो उससे कम B हो गया, sorry, so in that case the discriminant will become negative. Okay, so I'll have 1 should be equal to 8c by mv0 square b⁴. So b⁴ is 8c by mv0 square, and therefore the capture cross section area जो बोला गया that will be pi b0 squared, तो ये बन जाएगा pi times. All right, and c का वैल्यू भी हम सब्स्टिट्यूट कर सकते हैं. We had gotten a potential energy as minus k squared alpha q squared divided by 2r⁴, right? And I can just substitute k as 1/4 pi epsilon naught, and I'll get it as minus alpha q squared divided by 32 pi square epsilon naught square r⁴. And of course मैंने इसको c minus c by r⁴ लिखा, so c का वैल्यू मेरे पास आ जाएगा alpha q squared divided by 32 pi squared. ठीक है, and then just of course you can substitute it here and get the final answer. So that's the IPHO 2011 question. Honestly not a very difficult question, to be honest. अगर carefully किया जाए तो काफ़ी honestly इतना कुछ खास difficult नहीं था. Only thing was to recognize the pitfalls जहाँ पे वो कोई students P.T लेके potential energy लिख ले, whereas that is only valid for a constant dipole moment vector. And यहाँ पर भी वो deciding the sign of R minimum, तो वहाँ पे we had to take some special case. Otherwise the physics concept was quite straightforward of angular momentum and energy conservation. Okay, देख लो. Now I'm going to talk about a very rare concept that is rarely taught or even rarely known to people, that appeared in a beautiful paper in the American Journal of Physics in 2008, where we have a new conserved quantity when a particle is performing some motion under the influence of a fixed dipole. So I have the situation where I have a dipole, an electric dipole that is fixed. It is fixed, it cannot rotate, it is fixed at the origin, and I have some charge, point charge. Let's deal with the positive charge for now. So I have a charge of charge q and mass m, and to analyze the motion of this charge, there is a new conserved quantity that was that, like I said, that was given in the paper that came in 2008, and that conserved quantity is going to make our calculations very simple. Instead of doing by the standard method of writing all the tedious equations, we can use this conserved quantity to simplify our calculations. Let's take a look. So I have the charge at some instant, it is at a distance r and making an angle theta. Let's call this the x-axis and this is the y-axis. Right, and it has some velocity. So what I'm going to do is I'm going to calculate the torque by the electric field on this charge, and you'll see in a minute why I'm doing this. So what is the torque? See, we'll have a radial electric field and the tangential electric field. Only the tangential electric field will contribute to the torque. So torque about the origin would be R times the force, the tangential force, which is the charge into the electric field, right? Now this torque should be equal to the rate of change of angular momentum, correct? I can write my angular momentum as mr square into the angular velocity, which is the derivative of the angle theta. So this is the angular momentum of the charge about the origin. Here my dipole is fixed. So now I will just substitute E theta. What was E theta? Kp sine theta by r squared, where k is 1 by 4 pi epsilon naught. So let's just substitute that here. I'll get r cube. We have cube in the electric field. So when I substitute E theta here, you should see that we'll have kpq sine theta by r squared. Should be dl by dt. Now the trick is to create angular momentum on the left hand side. And I can do that just by multiplying m and theta dot. So if I just multiply m and theta dot in the numerator and the denominator becomes nothing but the angular momentum, which I can take to the right hand side. So I'll have kpqm sine theta dot should be equal to L dl by dt, right? Theta dot is the derivative of theta with respect to time, and I've taken this angular momentum to the right hand side. Now, can I write sine theta into theta dot? See what is the derivative of cos theta? Minus sine theta d theta by dt, correct? So I can just replace this, my derivative of cos theta. And L dl, can I replace it by the derivative of L square by 2, right? So now I can just club both of these terms and I can write a single derivative of L squared plus 2kpqm cos theta. And of course there is a, you can just divide it by 2, is 0, right? I've just taken this term to the right hand side and I've clubbed both the terms inside a single time derivative. So if the derivative of this term is 0, then that means that this term is a constant. And this is our new conserved quantity. That is not very obvious in the beginning. We had to do all of this calculation, arrive at this, but this will be very useful in our calculations. We'll see how. So this, the L squared plus 2kpq m cos theta is a constant. Alright, I've just absorbed this factor of 2 in the constant itself. So this is a new constant of motion. We already have energy as a constant of motion. We are assuming the motion of the charge in the 2D plane, in the xy plane. Okay, I'm restricting my motion of the charge to the xy plane for now. So in this situation, we have L squared plus 2kpq m cos theta is a constant. Alright, now we are going to look at how this conserved quantity will very much simplify our calculations in this general situation. So let me just erase this and then we'll proceed. So let me take a specific situation where I have a dipole and I have a charge here, let's say at a distance b at t equal to 0, and it is given a speed v0 and this is mass m, and the dipole is fixed. Alright, so I want to calculate the distance of the charge from the origin, from the dipole, as a function of time. Let's say that is my aim. So we are going to use the fact that we know that conserved quantity. So first of all, let me just write in the general situation where the charge is here at an angle theta and it has some velocity. So in this situation, can I write my energy as half m? See, I can write it as half m r dot square plus the perpendicular component of velocity. I can break down my velocity into the parallel component, which is r dot, and the perpendicular component, and then we'll have the potential energy, which would be kpq cos theta by r squared. This is my total energy, right? And as always, I'll substitute v perpendicular in terms of the angular momentum. I know angular momentum is mv perpendicular into r, so v perpendicular, this term I can just write it as L squared by m square r squared. Okay, so this will become half m r dot square plus L squared by 2 m r squared plus kpq cos theta by r squared. Now, L squared, we have a relation where L squared appears in a new conserved quantity, right? What was that? L squared plus 2kpmq cos theta was conserved. Let me call that conserved quantity as beta. Okay. And we know what in this specific example we know that value. I've still not used the specific initial conditions where the velocity is along the y-axis. I've not used that yet. This is still dealing with the general situation in the of the motion of a charge in the xy plane. Later we'll substitute, we'll use the information about the initial conditions to find beta, and then we'll solve the exact equation for r as a function of time. But for now, let me just substitute L squared, which is beta minus 2kpqm cos theta here. So let's see what the energy comes out to be, and it's going to be very much simplified, because once you do that, you'll have a term beta by 2mr squared, and then can you just see 2kpqm cos theta, if you substitute it here, 2m and 2m will get cancelled out. You'll be left with kpq cos theta by r squared, and we already have that here, and they'll cancel out, and that's it. This is we basically completely eliminated the explicit terms of theta and express energy purely in terms of r, which is a beautiful result, and it's not at all apparent before we actually figured out that this was a conserved quantity. It wasn't obvious at all. All right, so it's a wonderful result, and this is basically the result that we've been dealing with. If you go back to the very simple example where a charge is released from the initial position on the axis with some zero velocity, we used to get this equation. We used to get half m r dot square plus kpq by r square was the potential energy, kinetic energy and potential energy where the motion was 1D. In this example, you get the energy of this form. Mathematically, it is exactly the same as this, except that we have beta in terms of kpq. We have beta by 2m in terms of kpq. And therefore, we can use all the mathematical results that we got in this situation, in a very simple one-dimensional situation, here as well. So, can I just directly write? R is, now let's go to the initial conditions. So, my initial conditions are that R is B and R dot is 0. Alright, because initially the velocity is perpendicular to the position vector. So, the derivative of the magnitude of the position vector is 0, and therefore I can write R as R naught square plus V infinity square T square. I'm not deriving it again, we've already done it for the simple situation. So we have R is root of R naught square plus V infinity square T square, and all we have to do is R naught is B, the initial value of R, and what is V infinity? It is the value of R dot when R tends to infinity. So as R tends to infinity, this term goes to 0 and R dot goes to 2e by m, right? R dot square goes to 2e by m. And what is E? So E would be the initial energy is of course conserved, so we'll just use the initial value half mv naught squared plus the potential energy, which is kpq by b squared. Alright, so this will become V naught square plus 2kpq by R dot square initially is nothing, R dot square as R tends to infinity is nothing but V infinity squared. So we basically have the equation for R as a function of time. Okay. So it's a wonderful result that we have here, which is this is a conserved quantity, and this gives us a very simple expression for the energy in terms of R, and then this just mathematically reduces to the one-dimensional case that we've already dealt with. Alright, okay. Now let's look at an application of this in another example with a very interesting result, very interesting trajectory that this charge has under a specific initial condition. We'll just take a look at that. Let's look at a very interesting question, which was the analysis of this probably first appeared in, I think, 1996, if I remember correctly, in a paper in the American Journal of Physics. But we're going to analyze this in a different manner, different compared to the paper that appeared. We're going to analyze this using the conserved quantity that we have. So what is this? The setup is that we have a dipole and a point charge is released from the equatorial plane from rest. It's released from rest. So I want to analyze the setup, and the question can ask you what is the shape of the trajectory of the charge, and find the speed of the charge as a function of the angle traveled, or something of that sort. Okay. So once again we have the conserved quantity L squared plus 2kpmq cos theta is a constant, right? Now what is the value of this constant? Initially theta is 90 degree. Remember, theta is measured from the dipole axis, so theta is 90 degree initially, and it is at rest. So both these terms are initially 0. Angular momentum is 0 because the charge is at rest, and theta is 90 degrees, so cos theta is 0, and therefore the conserved quantity, this entire value, is 0 throughout the motion of the charge. Alright. Now at some general situation, remember this is the angle, we have to measure the angle from the positive, from the dipole moment vector. So of course cos theta will be negative, and that's why this L squared is a positive term and this is negative. Okay. So now if I look at the energy, I can write energy as half m r dot squared plus L square by 2 mr square. This was the term corresponding to the tangential component of velocity, right? And of course I'll have kpq cos theta by r squared, right? Now if I substitute L squared as minus 2 kpmq cos theta here, let's see what we get. What are we getting? Minus 2m and 2m will get cancelled out. I'll have kp cos theta by r squared. These two cancel out, and therefore the energy is simply half mr dot squared. So there is no component of the tangential component of velocity that's appearing in my energy. And that means because energy is conserved, that means r dot is also constant. Correct? And if r dot is constant, it should be equal to the initial value. What is the initial value of r dot? Initially the charge is at rest, so this is nothing but 0, and therefore the derivative of r is 0, therefore r is a constant, and r is a constant meaning the charge is always at a fixed distance from the dipole, and therefore the trajectory is a circle. Of course, the trajectory is going to be in this plane, that's why it's a circle. In 3 dimension, r is a constant, represents a spherical surface, but in this it should be obvious that the trajectory is only going to be in the xy plane. So the trajectory of the charge is a circle. Now it's all very straightforward. So r is always equal to b. What is the other thing that's being asked? Find the speed of the charge as a function of theta. So that's very straightforward. You can either use your energy. What is the energy? The total energy is also 0 of the charge because r dot is 0, right? So you can use your energy if you want, or you can use this conserved quantity, whatever you can use to get the speed. The speed is going to be perpendicular to the radius. The radius is a constant b now. So I can just conserve energy. Initial energy is, the total energy is 0, should be half mv squared plus kpq cos theta by b squared. And therefore v squared, or v, would be minus 2 kpq cos theta by b squared. Of course this is not imaginary because cos theta itself is negative, so of course we have a positive number inside the square root. I missed an m. Alright, so it's a very interesting trajectory, a very simple trajectory, and it's all simplified because of this conserved quantity. Okay. Now another interesting aspect of this particular example is that the motion of the charge is exactly like a pendulum. Let me talk more about that. In what respect it is exactly like a pendulum. Let me just talk more about that. Let me just erase this and let me compare this setup to our simple pendulum setup. Let me just rotate this diagram. Suppose this is X and this is Y. Let me just rotate the diagram such that the dipole is pointing in this manner, just for a nice comparison with the pendulum. So I have a charge here, mass m. Let me take another situation of mass m, of a particle of mass m connected by a string which is fixed at one end. All right, and this is released from rest. Now, as this charge travels, it is going to perform a circular motion. And of course, so is this. This is also going to perform circular motion. All right, it will come to rest here, and then it will keep oscillating. And that's what is going to happen to the charge as well. The charge started from rest. At this instant, when it reaches the equatorial plane again, the potential energy becomes zero, and therefore, because the total energy is already zero, the kinetic energy also becomes zero, and then it will again just keep oscillating. Right? The electric field is in the downward direction in the equatorial plane. So once the charge comes here, it will momentarily come to rest and then again retrace the circular path. Now, mathematically, both these situations are actually exactly identical. Why? Because if you look at, see, if this angle is theta, let me take this angle as phi, all right, so that we can deal with some acute angles instead of the obtuse angle. So at this point, when the charge is here, when the charge has rotated by an angle phi, what would be its speed? So I can just conserve the energy. So half energy was 0, so half mv square plus k p cube cos theta. Now cos theta I can write it as sin phi, minus sin phi, right? Because theta is pi by 2 plus phi. So cos of pi by 2 plus phi would be minus sin phi. So the speed comes out to be equal to kp, oh, I have missed out a charge here, so kpq sin theta by mb squared. Alright, so it is something, some constant, root of some constant into sin theta, right? Sin phi, sorry. Alright, the speed is square root of something into sin phi, right? What about here? If this mass travels, if the angular displacement is phi, if I just conserve energy, can I say mg into b sin phi is the work done by gravity should be equal to the change in kinetic energy? Once again, you get something into sin phi, some constant into sin phi. So mathematically, the motion is identical. All right. If you were to choose the parameters like 2kp cube by mb squared here, and here we have 2gb. In these two independent situations, if you were to just choose these parameters of maybe the charge, dipole moment or mass, so that this constant term and this constant term are equal, in that case, they will follow at exact time instants, they will have the exact same angular displacement. Because the speed as a function of phi would be identical in both the independent setups if you choose your constants to be equal. All right. So therefore, the time taken by the charge to reach the bottom would be exactly the time taken by this pendulum to reach the bottom. All right. The time period of oscillation will also be the same as this. Okay. So just an interesting setup here, and this is what was shown in the paper that came in 1996. But they did not use the. If I remember correctly, they assumed that the string was connected In this situation, they assume the string to be connected and they assume the charge is performing a circular motion, and then they showed that the tension was 0. That means even without the string, the charge will still perform circular motion, right? So they knew the result that the charge is performing circular motion and they proved it. And in our situation, we proved from first principles that the charge will indeed perform circular motion in this case using that beautiful result of the new conserved quantity. All right, so I hope you've understood this entire setup. All right. Now let's look at a question that I formulated after reading a paper from the European Journal of Physics in the setup where a charge is performing circular motion in the presence of a dipole, but that circular motion is in a plane that is perpendicular to the dipole moment. Alright, so let's take a look at the question and we'll solve it thoroughly. An electron of mass m and charge minus e revolves in a circular orbit with uniform speed under the influence of a point electric dipole of dipole moment having magnitude p pointing along the z axis. तो मेरे पास यहाँ पर ऐसे dipole moment है p and the plane of the orbit is parallel to the xy plane. अच्छा, तो इस तरीके से या इस तरीके से ऐसा कुछ इलेक्ट्रॉन रिवॉल्व कर रहा है. It's a center on the z axis. Magnitude of the electron's angular momentum is Lz. Okay. तो ऑप्शन ए और बी में क्या पूछा है? सेंटर ऑफ ऑर्बिट्स ऑन द पॉजिटिव z एक्सिस या पॉजिटिव ऑन या नेगेटिव z एक्सिस. तो सबसे पहले तो द force must be directed towards the center, correct? ऐसे होना चाहिए. तो जो डाइपोल है, डाइपोल का इलेक्ट्रिक फील्ड लाइन ऐसे जाएंगे, करेक्ट? तो यहां पर इलेक्ट्रिक फील्ड का जो कंपोनेंट है पैरेलल टू डाइपोल वो जीरो होना पड़ेगा यहां पर at the electron, right? Because it has only to have a xy component so that the electron does not move in the z axis. It's only traveling parallel to xy plane in a circular motion, right? तो वो दो पॉसिबिलिटीज है मेरे पास, या तो यहाँ पर कि इलेक्ट्रिक फील्ड यहाँ पर हो जाए या तो यहाँ पर. तो one plane is above the dipole and one is below the dipole. तो कौन सा लूप है? इलेक्ट्रॉन नेगेटिवली चार्ज है. I need the force towards the center, so the electric field must be away from the center. So this one. So the plane of the orbit must be above the z axis, मतलब above the dipole. ठीक है, मतलब above the dipole, above the origin. So positive z axis में होना पड़ेगा center of the orbit. तो ऑप्शन ए करेक्ट है. फिर ऑप्शन सी और डी में क्या पूछा हुआ है? एंगुलर मोमेंटम का वैल्यू. ओके, सो ये थोड़ा अपने को कैलकुलेशन करना पड़ेगा. लेट मी जस्ट इरेज दिस. सो डाइपोल का मुझे ये पता चल गया कि ऐसा एक एंगल पे है, ये इलेक्ट्रॉन सर्कुलर मोशन कर रहा है सच दैट सी आई हैव, अगर मैं यहाँ पर देखूँ तो मेरे पास एक रेडियल वेक्टर ऐसे है एंड एक टेंजेंशियल वेक्टर ऐसे है. रिजल्टेंट मस्ट बी इन दिस मैनर इलेक्ट्रिक फील्ड का, तो जाके फोर्स टुवर्ड्स द सेंटर आएगा, करेक्ट? तो यहाँ पर अगर मैं बनाऊँ, दिस एंगल इज थीटा, दिस इज ऑल्सो थीटा, दिस इज ऑल्सो थीटा, करेक्ट? सो कैन यू सी दैट रेडियल कंपोनेंट का z component and e theta का z component must cancel each other out. So e r cos theta must cancel out e theta sin theta, correct? So e r क्या होता है? 2kp cos, यहाँ पे cos square बन जाएगा, divided by r cube should be equal to e theta is kp sin theta, sin square theta by r cube. तो यहाँ से मेरे पास आ जाएगा tan theta is √2. ठीक है. अच्छा, यहाँ पे what is r? r is this distance from the dipole and मेरा radius को मैं capital R बोलता हूँ. Obviously capital R is r sin theta. Okay, so force equation लिखता हूँ कि E into the net electric field, which is this electric field, should be equal to mv square by r. अब net electric field को मैं क्या लिख सकता हूँ? That will be the xy component. तो ER का sin theta component प्लस ई थीटा, ये जो वेक्टर है ये वाला, उसका कॉस थीटा कंपोनेंट. तो देखो क्या बन जाएगा, ई आर इज 2kp कॉस थीटा, तो कॉस थीटा इनटू साइन थीटा एंड ई थीटा इज kp साइन थीटा. सो ये बन जाएगा 3kp साइन थीटा कॉस थीटा बाय आर क्यूब. ठीक है. सो आई विल राइट 3kpe साइन थीटा कॉस थीटा बाय आर क्यूब लेफ्ट हैंड साइड पे शुड बी इक्वल टू एम वी स्क्वायर बाय, अच्छा एक मैंने मिस्टेक किया यहाँ पर स्मॉल आर नहीं होना चाहिए, रेडियस होना चाहिए ना, तो इट शुड बी कैपिटल आर। ठीक है, सो लेफ्ट हैंड साइड पे लेट मी राइट स्मॉल आर एज कैपिटल आर बाय साइन थीटा, तो ये नीचे यहाँ पर आर क्यूब बन जाएगा एंड ये साइन रेस टू 4 थीटा बन जाएगा। ठीक है, सो अब देखते हैं, ये एक आर यहाँ पे कट के यहाँ पे आर स्क्वायर बचेगा, सो आई कैन राइट एम वी स्क्वायर आर स्क्वायर शुड बी इक्वल टू 3 पी ई साइन रेस टू 4 थीटा इंटू कॉस थीटा। ठीक है, एंड अगर मैं m से मल्टीप्लाई करूँ दोनों तरफ तो मेरे पास लेफ्ट हैंड साइड पे एंगुलर मोमेंटम का z कंपोनेंट का स्क्वायर आ जाएगा। सो राइट हैंड साइड पे क्या आ जाएगा 3 अभी बस सब्स्टिट्यूट करते हैं, tan थीटा √2 है तो sin थीटा का वैल्यू कितना बन जाएगा √2 बाय √3 एंड cos थीटा का वैल्यू बन जाएगा 1 बाय √3। करेक्ट, तो साइन रेस टू 4 थीटा मतलब क्या बन जाएगा, साइन रेस टू 4 थीटा वुड बिकम 4, so sin raised to 4 theta will become 4 by 9, correct, and cos theta would become 1 by √3 into m। ठीक है, तो ये एक 3 और 3 यहाँ पे कट गया, so LZ would become 2 by 3√3 का स्क्वायर रूट into स्क्वायर रूट ऑफ KPEM and 3√3 मतलब 3 raised to 3 by 2 and फिर से स्क्वायर रूट लेंगे तो 3 raised to 3 by 4, सो डिनोमिनेटर में आ जाएगा 3 raised to 3 by 4 एंड ये k को मैं 1 by 4 एप्सिलॉन नॉट लिख सकता हूँ, सो द आंसर मैचिंग वुड बी C। ओके, सो A and C will be the correct answer।
Let's look at an interesting question. So मेरे पास एक चार्ज फिक्स्ड है and at a distance r0 I have a small dipole जिसका length is much lesser than r0। ठीक है, so ये जो length है is much lesser than r0, so it consists of minus negative charge and positive charge and दोनों का मास m दिया गया है। ओके, एंड इस डाइपोल को उसके सेंटर ऑफ मास को एक वेलोसिटी देते हैं vcm परपेंडिकुलर टू द डाइपोल एंड एक एंगुलर वेलोसिटी भी देते हैं such that you can say that the charges are connected, the charges of the dipole connected by a massless rod, ये मान सकते हो। ठीक है, तो ये जो सिस्टम है मेरा डाइपोल है उसके सेंटर ऑफ मास को एक वेलोसिटी दिया जाता है इनिशियली परपेंडिकुलर टू द डाइपोल मोमेंट एंड एक एंगुलर वेलोसिटी भी दिया जाता है such that the dipole moment vector is always points, ये हटा देता हूँ, always points radially away from this charge q। okay, so dipole moment vector always points radially away from the charge q। okay, so let's solve this question। तो at some instant let's say कुछ distance r है, तो ये मेरे पास माइनस क्यू है, ये प्लस क्यू है, जो अपने को क्वेश्चन में दिया नहीं गया है, वी आर जस्ट गिवन द डाइपोल मोमेंट p। ठीक है, तो कैन यू सी दैट द फोर्सेस, द एक्सटर्नल फोर्सेस इज अ कूलम अट्रैक्शन हियर एंड द कूलम रिपल्शन बाय दिस चार्ज कैपिटल क्यू, राइट। तो अगर मैं टॉर्क इक्वेशन देखूँ अबाउट द सेंटर ऑफ मास, तो अबाउट सेंटर ऑफ मास torque is 0, so इसका मतलब the angular velocity must be constant। moment of inertia तो change नहीं हो रहा about center of mass, correct, so angular velocity must be constant। now angular velocity अगर constant है तो इसका मतलब see because the rod is rotating at a constant angular velocity and the rod is always radial, so that means ये जो position vector है उसका rate of rotation should also be the same angular velocity, d theta by dt should also be equal to omega because this rod is always parallel to the position vector, correct। so अगर मैं point q के about देखूँ, torque about the charge q, the torque of the electrostatic forces on minus q and plus q is again 0 because they are both passing through q। So angular momentum about Q, angular momentum of the dipole about Q is a constant, correct? अब angular momentum about Q is a constant, angular momentum को मैं क्या लिख सकता हूँ? अगर I can write it as, for this minus Q charge I can write it as m कुछ r minus बोलता हूँ उसका distance, so this is r minus into ओमेगा प्लस इसका m r plus square omega is a constant, correct? इसका मतलब r minus square plus r plus square is a constant because omega constant already हमने प्रूव कर दिया यहाँ पे, करेक्ट? एंड r माइनस को मैं क्या लिख सकता हूँ? अगर ये डिस्टेंस कुछ d मान लो है, r जो है दैट इज द डिस्टेंस फ्रॉम q टू द सेंटर, दिस इज r माइनस, तो r माइनस को क्या लिख सकता हूँ? r माइनस d by 2 and r plus would be r plus d by 2 the whole square is a constant. इसका बेसिकली मतलब कि r itself is a constant. And that just concludes जो शायद फील ऑलरेडी आ चुका होगा कि the dipole has to perform circular motion, uniform circular motion. Why uniform? Because omega constant है, r constant है, तो VCM will be equal to omega r now. This is VCM, correct? So VCM भी constant है. Alright, so the dipole is performing uniform circular motion about the point charge Q. So now let's write the circular motion equations, and now it's pretty straightforward. So let's write the force equation कि मेरे पास यहाँ पे एक चार्ज है and ये dipole है, तो कितना फोर्स लगेगा? डिस्टेंस तो r नॉट है दोनों के बीच का, तो how do we calculate the force by a dipole on a charge? I can write it as the field of a dipole on its axis, which would be 2kp by r cube into the charge. ठीक है, so ये मेरा फोर्स बन जाएगा between the dipole and the charge, and this force 2kp cube by r naught cube should be equal to ये जो दो masses है यहाँ पर dipole के m and m. लेट्स सी ये डिस्टेंस कुछ r माइनस है नेगेटिव चार्ज का एंड पॉजिटिव चार्ज का डिस्टेंस r प्लस है, तो आई कैन राइट इट एज m ओमेगा स्क्वायर r माइनस प्लस m ओमेगा स्क्वायर r प्लस, राइट? सो आई कैन राइट इट एज 2m ओमेगा स्क्वायर r माइनस प्लस r प्लस बाय 2. सो बेसिकली द एवरेज ऑफ द डिस्टेंसेस विच इज नथिंग बट r नॉट, राइट? ये तो सेंटर ऑफ मास का डिस्टेंस हो गया, सो मैं लिख सकता हूँ 2kpq by r naught cube should be equal to 2m omega square r naught. तो यहाँ से अपने को ओमेगा का वैल्यू आ जाएगा, तो ये बन जाएगा kpq डिवाइडेड बाय m r naught raised to 4. Okay, so that's your angular velocity, and center of mass का velocity कितना होगा? That will simply be omega r naught. Alright, so it's an interesting question where first we had to deduce कि the dipole is going to perform circular motion. देख लो.